Learning multi-view spatial reasoning from cross-view relations. We introduce CVPR, a large-scale dataset designed to teach vision-language models spatial reasoning across multiple views. Multi-camera setups are now widely used in robotics. Systems such as large behavior models, AGI bot world, and Droid all rely on multiple camera viewpoints, as shown in these examples. This makes understanding cross-view relations critical for enabling effective manipulation and navigation. Even state-of-the-art models struggle with multi-view spatial reasoning. In these two examples, models must identify temporal misalignment on the left and matching camera viewpoints on the right. Only GPT-5 succeeds in the first task, and only Gemini Robotics in the second. These failures show significant gaps in understanding cross-view relations. To address this limitation, we introduce cross-view relations, or CVPR. Consider this sample scene with 4 cameras. We design 3 categories. Correspondence identifies matching elements, verification validates consistency, and localization reasons about camera relationships. These categories expand into 8 specific tasks across 100,000 samples. The correspondence category includes point and directional tasks. Both require identifying matching elements across multiple reference views. The verification category includes spatial and temporal tasks. Both detect inconsistencies, either geometric or temporal, across views. The localization category includes 4 tasks: viewpoint, directional view, cross-scenario, and language conditioned. All require reasoning about camera positions and their spatial relationships. CVPR uses 2 complementary sources. The general domain from WildRGB-D provides accurate camera calibration for geometry-based tasks. The robotic domain from OXE and AGI bot world provides temporal continuity and viewpoint diversity from manipulation trajectories. Together, these provide the precision and diversity needed for cross-view reasoning. We develop a unified generation framework that operationalizes cross-view relations by structuring raw, multi-view data into concrete question-answer pairs. For the general domain, we employ 3D to 2D projection using explicit geometry. For the robotic domain, we sample from spatiotemporal metadata and temporal indices from robotic trajectories. Using this pipeline, we generate 100,000 cross-view relations VQA samples. We fine-tune Quen 3VL2B on CVPR. Here's a training example. Identify the temporally misaligned image. The answer is image 3. This is how we provide explicit supervision on cross-view relations. We evaluate on CVPR eval, a held-out benchmark of 1,866 samples from unseen data sources. Our model achieves 68.06% accuracy, 1.8 times better than the base model, and ranking first among all evaluated models, substantially closing the gap to human performance. CVPR also transfers to external benchmarks. MindCube Tiny tests multi-view reasoning. We see gains across all tasks. RoboSpatial Home tests robotic spatial understanding. CVPR improves both compatibility and configuration. Cross-view training benefits even single-image spatial reasoning. To investigate the benefits of CVPR on embodied tasks, we extend VLMs trained on CVPR into vision-language action models. We add a diffusion action head for robot action decoding and compare a baseline using Quen 3VL2B against our CVPR-trained backbone, with both using the same action head architecture. Using the RoboCasa simulator, we evaluate 3 manipulation tasks. Coffee press button improves from 83.1% to 89.3%. Turn off microwave shows a dramatic increase from 45.7% to 72.7%. PNP cab to counter improves from 31.1% to 38.8%. These consistent gains across diverse manipulation scenarios demonstrate that cross-view relation reasoning effectively transfers to robotic control. To summarize, we introduce CVPR, which provides explicit supervision on cross-view relations for multi-view spatial reasoning. The dataset contains 100,000 multi-view QA samples structured into correspondence, verification, and localization. Training on CVPR improves out-of-distribution spatial benchmarks and VLA manipulation performance. Thank you for listening.